So in Chapter 12, we're going to learn how to appropriately collect a sample so any survey results will accurately represent the population of interest. To start, let's refresh on some vocabulary that we've gone over in the past, but we may have forgotten. When we refer to a population, we're talking about everyone that we're interested in. Okay, when we refer to a sample, we're talking about a group of that population or a part of the whole. Okay, now in this chapter, we're going to be drawing a sample from a population, asking that sample a certain number of questions, and using their responses to get an idea of what the whole population thinks about a subject. Now, sampling is a very natural thing to do. Okay, if we want to apply it to cooking and to making a soup. Okay, if we make a soup, we don't have to eat the entire pot of soup to see if it tastes good. We can just take a spoonful. Right? What's important prior to actually tasting the soup is that we stir it. Okay, stirring it is the equivalent of randomizing our sample. All right, so when we stir the soup, we're randomizing all the ingredients, we're mixing them, making sure that when we take that spoonful, we're getting a taste of everything in the soup. Okay, randomization, like we learned last chapter, is a very important part of this chapter. Okay, and if we have a random sample, we're going to get a sample that's representative of the whole population, meaning that our results are going to match what we would get if we took like a full census of everyone in the population. Now, there are a lot of ways that we can mess this up. Okay, there's a lot of things we can do wrong in sampling, and we'll get to some specific examples towards the end of our notes here. But for now, we're just going to say that when we have a sample that's not representative of the population, that sample is said to be biased. Okay, it's not going to match the population results for some reason or another. Once we have a biased sample, there's really no way to fix it. And the best way to protect against the biased sample is to select sample respondents at random. So the concept of randomization is important not just for this chapter, but really the entire course moving forward. And the reason being is that when we randomize, it protects us from all of the influences in the population, even ones that we may not have thought about. This is really something that we're going to discuss more in class rather than spend the time here in the notes because it would just take too long. For now, the key point is that randomizing makes sure that on average, the sample looks like the rest of the population and isn't biased towards one subgroup or another. One thing that's a bit counterintuitive when it comes to sampling is how large of a sample we need when it comes to getting an idea of what the population feels about a certain subject. Let's apply it to political polling since that's where most of you are familiar with this subject. So let's say we have 3 races we want to poll. One of them is the mayor of Toms River. Then the other is the senator of New Jersey. And then the third race we want to poll is for the president. Okay, Toms River has a population of around 70,000. New Jersey has a population of around 7 million. And then the United States has over 300 million people in it. In all 3 of these situations, we can poll 2,000 people and get an idea of how all 3 of those races will turn out. The counterintuitive part of that is that we would expect with the population increases, we would require larger samples. For example, switching from a 70,000 population town to the 7 million population New Jersey, we would have to go from a 2,000 sample to a larger one. That's not true. It's actually the size of the sample, not the size of the population, that makes the difference. Okay, there are certain exceptions to this, which we'll get to in later chapters, such as this one right here. All right, we don't really need to discuss those quite yet, but they are noted there. Now, one question is, why take a sample at all? Why not just perform a census where we'd actually go and talk to every single person in a population? Let's apply it to a race for Toms River mayor. In that case, we'd want to go to every door or call every person in the township and ask them, who do you plan to vote for? That would give us not just an accurate representation, but an exact representation of how people plan to vote. Okay, now, a census isn't always practical. First off, it'd be very time consuming. Okay, it would be very difficult to complete. Okay, there's certain people that would be really hard to track down. They're not likely to answer their phones. They might not be home if we're going door to door. And along with that, populations rarely stand still. Some people are moving into town, some people are moving out of town. So by the time we take to actually complete the survey, the sample, or in this case the census, I'm sorry, it's likely that that population has changed and it's no longer an accurate census. Now for some more vocabulary. When we're dealing with populations, if we have a numerical quantity that has to do with that population, we label that a parameter. Okay, if we have a numerical quantity that has to do with a sample, we label that a statistic. Okay, P's go with P's, S's go with S's. On these next few slides, we're going to discuss the different types of samples, with the most common being referred to as a simple random sample. This is the equivalent of where we take everyone's name and we put into a hat, and we randomly draw names from the hat. The important thing to note about a simple random sample is that we can end up with any group of people. Now I'm discussing this as an example of pulling names from a hat, but we can just as easily do this with numerical data, drawing numbers and then averaging that data to get a single value. Now if we do this numerous times and each time we average those values, we'll get different averages across different samples. Okay, that makes sense because each time we draw a different sample, we'll be getting different numbers. Okay, we wouldn't expect to get the same average every time. Okay, these different sample averages is referred to as sampling variability. Okay, the larger the sample, the closer they'll be, right? But it's not surprising to get different values from different samples. In stratified sampling, we first break the population into groups or strata, such as gender, location, race, etc. We then do a simple random sample within each group before combining the results. As an example, let's say we wanted to take a sample of 100 high school South students and ask them how they felt about the schedule for late buses. If we were to take a simple random sample, maybe we would get 75 seniors of those 100 students, okay? Because remember, in a simple random sample, we can end up with any group of 100 students. That's too many seniors. Seniors might not care about late buses because most of them drive, right? So instead, we might be interested in doing a stratified sample where we break them into their grade level, okay? In this case, we would first separate them freshmen, sophomores, juniors, seniors, and take 25 of each selected using a simple random sample. Okay, this helps us because it's going to reduce the variability within our samples, right? Especially if we take multiple samples, we're always getting 25 freshmen, 25 sophomores, etc., etc. So we'll get more consistent results across different samples. Okay, it also helps us because we'll notice any differences within those groups. Okay, if freshmen have different opinions than sophomores, than juniors, than seniors, we'll be able to actually break those out and look at those individually. Cluster sampling is similar to stratified sampling in the sense that, again, we have different groups, right? But it's slightly different and it's easy to confuse. Okay, let's say we have a different question. In this case, we want to ask high school South students how they feel about the process of creating their schedules for the following year. Rather than sample them stratified like we did in the last slide where we broke them into grade levels, we want to pick a single group, and to simplify the process of the sampling, we want to just take that group and perform a census on that whole group. So in this case, let's say we pick a single period, we go into the gymnasium and we survey everyone in the gymnasium as to how they feel about the scheduling process. Okay, this would be a cluster sampling. We're picking one group, we're sampling everybody in the group. Compare that to the last slide, we broke freshmen, sophomores, juniors, seniors into separate groups, and we performed a simple random sample of each of those. Okay, so we stratify, which we did on the last slide. When we have different groups, like those different grade levels, we make sure that they're all represented in our final sample. We do a cluster sample, okay, when we have groups that are largely the same. So in this situation, we're assuming that each period, the gym classes are going to be largely the same, largely representative of the whole school population. That may or may not be true, all right, but that's the assumption. So we're just going to pick one period and survey everyone in the gymnasium. Unsurprisingly, these types of samples are not always done on their own. Sometimes they're combined, and when they are, we refer to them as multi-stage samples. Lastly, we have systematic samples. This is where we, for example, would survey every 10th person on an alphabetical list or every 25th person as they enter the school in the morning. The key thing to remember is that we always have to have some kind of randomization. So the randomization for a systematic sample would be which student that you start with. For example, we would say we randomly select the number 3, we start with a third person, and then we select every 10th person on the list. Okay, or we randomly select the number 12, we start with a 12th person, and then we select every 25th after that 12th person as they enter the school. Every valid method of sampling must incorporate some form of randomization, right? That's what protects us from biases. Here we have some example problems. Go ahead and pause the video, read this problem, attempt to answer it on your own, and then resume it when you're ready to go over it. So we want to pick some random passengers from this flight. In part A, we're doing a systematic sample. We're picking every 10th passenger from these 300 people. Okay, just keep in mind that for this to be an effective sampling method, we do need to randomize which passenger we start on. Part B, we have a stratified sample. The reason being is that we have two different groups of passengers. We have the first class passengers, and then we have the other passengers. We're ensuring representation from both groups, so we're picking 5 randomly from that first class group, and then 25 randomly from the rest of the passengers. C would be a simple random sample. Here we're just randomly selecting 30 seat numbers and surveying those passengers. We can end up with any 30 passengers. It's possible that all 30 will be male. It's possible all 30 will be senior citizens. Maybe they're all window seats. Maybe they're all first class. Right? There's no restrictions on the 30 people that we could ultimately end up with in a simple random sample. And then lastly, D would be a cluster sample. In this case, we're choosing a group, with the group being the seat position on the plane. We're assuming that that group is representative of the whole plane, and then we're surveying every passenger in that group. When it comes to describing sampling plans, we want to explain the W's of the problem, but most importantly, we want to describe the randomization. We're going to go through this in detail in some sample problems during class, but for the most part, we treat this like we did with explaining the randomization for simulations in Chapter 11. One of the tricky things that can come up when you're explaining the W's is defining the who. Okay, and this ties into what's called the sampling frame of the problem. Okay, let's tie it back to polling for an election, right? When a reputable polling firm contacts people for an election, right, they'll contact a number of people, all right, and the first question they ask is, are they registered to vote? Okay, so that's the first filter they apply, right? They get a number of responses from those people, okay? Now, those people are not necessarily all going to go out and vote on election day, okay? What they actually want are responses from likely voters. So all these registered voters are asked a series of questions such as, how likely are you to vote from 1 to 10? Did you vote in the previous election? Do you know where your polling place is, etc.? Okay, and that leads them to decide whether or not this specific person is likely to actually cast a ballot for the preferred candidate. Okay, this would result in them being included in the final sample. Obviously, there's a number of ways we can sample incorrectly, with the most common being called a voluntary response sample. In a voluntary response sample, respondents opt in to responding to the sample. In other words, they're not required to respond. They can decide whether or not they want to participate in the sample. Examples of this are calling into a radio show or clicking on a link on a web page and participating in an online sample that way. Voluntary responses are often biased towards those with strong opinions. The people who click those links or call into call into radio shows are ones that care very strongly, either in favor of or against the issue that's being polled. Convenience sampling is another way we can sample badly. This is where we get samples from people who are easy for us to get responses from. For example, if we go to our friends and family for responses rather than actually going through the trouble of getting a simple random sample or including any kind of randomization. A bad sampling frame, the most common example or easiest to explain is using a registered versus likely voter frame in a political poll. Okay, as we actually filter down to that likely voter, becomes more specific. But if we just poll people, say at a movie theater, it's not actually going to be the correct sampling frame. There's also something called undercoverage, where a portion of the population is not represented as much as they should be. An example of this would be if we polled people by calling numbers in the phone book. People who have cell phones and don't have landlines, which are the numbers that are listed in the phone book, would be undercovered. Okay? And these people are most likely to be younger than the people who actually are listed in the phone book. The final two issues we want to address about sampling is we want to be careful about non-response bias and response biases. Non-response bias is when we're taking a poll and there's certain people that are not responding. Let's say that we have someone who's canvassing a neighborhood, they're knocking on doors, and there's certain people who are just not answering. Maybe it's because they're at work, so we're getting answers from all the people who are at home, and maybe we're missing people who are more likely to be at work or working a second job, and we're more likely to get responses from people who are, say, retired or have enough income to stay home for whatever reason. That would be a non-response bias. A response bias refers to anything that would influence the responses of the people. For example, if I were to give you a survey about how well you liked the statistics class or my teaching method, and you knew that that survey was going to get returned to me, there would be a response bias in your answers. You'd most likely not be completely honest knowing that those responses were being returned directly to your teacher. Okay, anything that affects responses in a survey would be considered a response bias.